Ready to rethink light? Imagine a photon not as a simple quantum, but as a composite particle with internal oscillations that challenge the classic energy-frequency law. De Broglie's groundbreaking ideas suggest particles bear intrinsic oscillations. Extending this, the composite photon model unites classical motion with quantum mechanics, sparking fresh insights. The model incorporates the relativistic Doppler effect. As internal oscillations shift frequency with motion, observed photon energy appears doubled, revealing complexities beyond standard laws. To harmonize theory with observation, modifications to the Schrödinger equation rescale energy quantization. This adjustment aligns with reduced photon energy and classical electromagnetic constraints. Crucially, this approach resolves the spin-orbit coupling anomaly naturally. By halving the photon energy, atomic spectral deviations vanish, affirming the model's validity. In conclusion, the composite photon model challenges traditional notions and invites further experimental exploration. Its blend of classical and quantum insights paves a transformative path in physics research.
The paper we're diving into today is Composite Photon Energy Frequency Relation, revised 6 February 2019, and it's by David Lush. I have to say, this was not your standard run-of-the-mill quantum mechanics paper.
No, not at all. I mean, just from the title, you know you're in for some fundamental questions about what a photon actually is. Honestly, when I first saw it, I thought, okay, another tweak on E equals Vovac. But it goes way deeper than that.
Exactly. So the core question that Lush is tackling is, does the energy of a photon really have to be E equals h nu, that is, Planck's constant times the frequency? Or, if we imagine the photon as a composite, meaning made up of two tiny, oppositely charged, spinning particles, does that change the relationship in a meaningful way?
Yeah, and this is pretty significant because, well, you and I grew up with the idea that the photon is this indivisible quantum of light, massless, just pure energy zipping through the void. But Lush asks, what if that's actually not the whole story? What if photons actually have a little internal structure? If true, it could change how we think about blackbody radiation, quantum mechanics, all of it.
So maybe let's explain for a sec what he means by massive composite photon. This is not what most physicists believe. Normally, photons are considered elementary and massless. But Lush says, imagine a photon as two classical charges, like tiny, oppositely charged particles, spinning around each other at nearly the speed of light.
And then he uses this setup to try to explain the energy-frequency relationship of photons. Turns out, it almost hits Planck's E equals h nu, but not quite. According to his calculations, the energy is actually closer to h nu divided by 2, that is, E equals h nu over 2.
Exactly. And he says this factor of half isn't just a random mistake or some technicality. It actually emerges from the way the electromagnetic field would oscillate thanks to this spinning motion and from the relativistic Doppler effect, which, by the way, is the same effect that makes stars appear red or blue when they're moving toward or away from us, depending on the frequency shift.
And this is where it gets interesting. Lush points out that, in this composite model, the photon energy comes out to h nu over 2, regardless of the mass or charge of its supposed constituents. And he connects this to Planck's blackbody spectrum, the classic formula about the spectrum of light emitted by a hot object.
Yeah, he argues that Planck's original theory assumed standing wave modes, which don't have momentum. Photons, on the other hand, do. So, Lush suggests, maybe each energy quantum that Planck described is really made up of two photons, each carrying only half the energy we traditionally assign them.
That's wild, right? It kind of flips the standard quantum picture on its head. So, in Lush's view, the photon isn't the basic quantum of electromagnetic field energy, it's sort of half a quantum, so to speak, and you need two to make a Planck quantum.
Right. So what does he do with all this? Well, he applies it to a couple of big quantum puzzles. One is the so-called spin-orbit coupling anomaly, where the energy differences in atomic spectral lines are off by a factor of 2 from what classical models would predict.
Yeah, and physicists normally patch that up with something called Thomas precession, which is this relativistic effect you see in spinning particles. But Lush says, look, if you accept this halved photon energy, you don't need a complex precession effect to fix the math. You just get the right number straightforwardly.
Honestly, I see the appeal of a simpler solution, but I'm not sure this composite photon model would work with everything we know about quantum electrodynamics, or even about photons themselves not having mass. I mean, experiments consistently suggest the photon's mass is vanishingly small, if not zero.
I get that. And Lush kind of admits that his approach is speculative, a new way of framing old issues. He does tie it back into the historical development, like how de Broglie first imagined wave-like matter and struggled with frequency relations. There's an almost poetic symmetry in reversing that logic for photons themselves.
Can I digress for a sec? I once read that someone tried to define a massive photon to explain why you sometimes get light bending a bit more than expected in plasma. But the results never quite lined up, and you end up with limits on photon mass that are so tiny they're kind of mind-boggling.
That's a great tangent.
The paper we're diving into today is On Einstein-Minkowski-Osiak Relativity by David Lush.
Okay, that's quite a title, right? I feel like just saying it out loud almost makes me smarter. But yeah, so this paper by David Lush is basically revisiting, well, challenging actually, some of the key ideas we all thought were settled in relativity.
The core question is, honestly, a wild one. What if the textbook version of Einstein's relativity isn't the only game in town? Lush explores an alternative called Osiak relativity that's based on different mathematical assumptions. Specifically, it argues that if you base your descriptions of particle mechanics on fully Lorentz-invariant Minkowski equations, so four-dimensional equations, rather than the usual three-dimensional Planck ones, you actually get different formulas for energy.
And it's not just some subtle difference. It literally changes what the rest energy, kinetic energy, and total energy of a particle are supposed to be. Apparently, in this Osiak version, the rest energy is E0 equals mc squared by 2, instead of the classic E0 equals mc squared.
Yeah, which, if you love your Einstein posters and mugs, kind of hurts, right? I mean, E equals mc squared is like the most famous equation in physics.
I know! But the significant thing here is, Osiak relativity doesn't conserve energy in relativistic collisions the way Einstein's version does. Instead, it preserves something called the temporal component of 4 momentum. So, for all practical purposes, like the energy thresholds that smash particles together, they still come out right, but the underlying principle isn't energy conservation, it's temporal momentum conservation.
That is a lot to wrap your head around. I love that nerdy distinction, though. It's a reminder that the universe doesn't care about what's in our textbooks. But back up. Does this mean all the observed conservation laws are just aspects of momentum conservation in this framework?
Pretty much, yeah. If Osiak relativity accurately describes nature, then what we've been observing and calling energy conservation is actually a reflection of 4 momentum conservation. Which, honestly, makes me a little dizzy, but...
No, same. Because that's like saying all of these collision experiments we've done, all of physics built on those, maybe our explanation's been wrong, even if our calculations lined up. It's very, you've been using the right recipe, but you don't understand why it works.
Exactly. And Lush really stresses that this isn't just theory for theory's sake. Like, he mentions possible consequences for dark energy and dark matter. That if energy isn't strictly conserved, maybe that missing energy we attribute to dark energy or dark matter is just, the universe not keeping the kind of books we expected.
I mean, it would be kind of poetic if dark energy was just the universe bungling its accounting.
Or being way more clever than our equations. Oh, also, this is a fun side note, and then I promise we'll get back on track. Lush goes off about how, under OSIAC relativity, the electromagnetic field should be complex valued, not just real, which could maybe connect to why quantum mechanics uses complex numbers everywhere.
Yeah, that's wild. Like, maybe the math weirdness in quantum stuff isn't just quantum is spooky. Maybe it's just our relativity being incomplete.
And to make it even more spicy, OSIAC relativity resolves some persistent puzzles, like the spin-orbit coupling anomaly in atomic physics. In this new framework, the energy levels just make sense without introducing things like Thomas precession, which always felt kind of like a fudge to me.
This brings up a meta point, actually. One thing I keep coming back to, reading through this paper, is how scientific theories aren't absolute truths. They're frameworks. And sometimes we find out the framework we've been using is kind of off. But if it still made good predictions, should we care? Or should we push for something more fundamental, whatever that means?
Yeah. Like, does it matter if it's momentum or energy being conserved, as long as a collider produces the right amount of stuff? Maybe it only matters when we want to explain something that doesn't fit, like dark energy.
And honestly, listeners, that's the kind of philosophical rabbit hole academic research leads us down. Lush isn't claiming he's found the truth, but he's showing that there's more to explore. And sometimes that means turning long-cherished ideas on their heads.
If anything, it's a good reminder not to take textbook physics as unchanging gospel. The real universe might still have surprises up its sleeve, just waiting for someone to reconsider what everyone else took for granted.
Absolutely. The paper we're diving into today is Dark Matter as the Difference of Inertial and Gravitational Mass by David Lush.
Yeah, and wow, what a title, right? Dark matter as the difference of inertial and gravitational mass. It already hints this isn't your usual let's find a weird new particle approach.
Right. So the core problem Lush is addressing is the whole dark matter mystery. You know, galaxies spin way too fast to be held together by just the visible stuff. Stars, gas, dust. For decades, we've wondered, what's this invisible, dark matter giving them their extra gravitational glue?
But here, Lush comes at it from a totally different angle. Instead of inventing new matter, he's basically saying, well, maybe the laws we use to add up mass, inertial versus gravitational mass, need a rethink. That's pretty wild, because, in physics class, weren't we taught those two are always equal?
Exactly, and that's key. So he's questioning something fundamental. Lush builds his argument by combining two unconventional theories. One is OSIAC's tweak on special relativity, and the other is the Harari-Shoup model, which says that even the building blocks of matter, quarks and leptons, are made of even tinier things called preons.
Yeah, that preon thing is wild. In the Harari-Shoup model, every elementary particle is basically a combo of just a few types of preons and antipreons. So, at that level, matter and antimatter are thoroughly mixed together, which is not what we usually think.
Right. So, if you take that and then bring in OSIAC's alternative relativity, which, among other things, apparently allows different ways of adding up energy and mass for composite systems, suddenly you can get situations where a lump of matter's gravitational mass, the amount it pulls gravitationally, is different from its inertial mass, the amount it resists being pushed.
Okay, so you're saying that in this hybrid theory, a hunk of matter might weigh more gravitationally than it weighs when you shake it or put it on a scale?
Exactly. And that might sound bizarre, but Lush argues that we only measure mass via inertia, or the weight in the local gravitational field. But if these quantities diverge because of this preon-antipreon mix, we could be underestimating the true gravitational mass of, say, a whole galaxy.
So under this model, when astronomers measure the mass of galaxies using stars' orbits, the numbers seem too low. but that's because they've been using the wrong version of mass all along?
That's the idea. If we've been equating inertial and gravitational mass, but in reality, gravitational mass is higher, then the so-called missing mass, the dark matter, is just this difference. It's not made of exotic new particles, it's baked into the fabric of what we already have.
One thing that fascinated me was that Lush even tries to estimate the ratio of dark to visible matter by tallying up preons and antipreons in a typical atom, like deuterium, and he ends up getting numbers that aren't far off the dark to visible matter ratios we see in observations, like 6:1.
I mean, it's definitely a hand-wavy calculation. He even admits that. But the fact that it lands in the same ballpark is, at the very least, pretty suggestive. But of course, these models aren't mainstream.
No, but it kind of gives you a different feel for what academic research means, right? Like, it's not that he's claiming absolute truth, it's more, here's a framework, here's a way to see familiar problems from a new angle, and if it sparks an experiment or a new analysis, then awesome.
True, and he does mention possible ways to test it, like if you could somehow make highly precise gravitational constant measurements with test masses of radically different composition, you might see tiny differences. That would give a clue.
That reminds me of, I don't know, sort of like the early days of atomic models, when you know you're missing something, but you're not sure where the fudge factor is yet.
Or like when people first suggested the neutrino to explain missing energy in beta decay. At the time, maybe it seemed desperate. Now it's basic knowledge.
You know, I think I read somewhere that most dark matter searches have been looking for new particles, and, well, nothing so far. This paper offers a reality check. Maybe we're barking up the wrong tree?
Or at least, maybe we shouldn't rule out wild alternatives.